This is the 8th lecture in this course and the 6th lecture on equilibrium carrier concentration. We have been discussing on the carrier concentration of intrinsic semiconductors. First we discussed the qualitative model, and in the last two classes we have been discussing the quantitative or the band model. The summary of the model that we discussed so far, the band model, is that you have allowed energy levels in a crystal which looks something like this. So an allowed conduction band, let us say this is the top of the conduction band, separated by another band, that is the valence band. This is the bottom of the valence band. So this is the conduction band and this is the valence band, separated by an energy gap. Then the valence electrons in the crystal occupy the valence band at t equal to 0, some of these electrons may go up to the conduction band when you raise the temperature. So all the valence electrons at t equal to 0 occupy the valence band. Now how are the electrons, the states for these electrons distributed? We have shown that the distribution of the states is something like this. That is the function Ne. And this area indicates a total number of states in the valence band, and that is 4 valence electrons for each of the 5 into 10 power 22 silicon atoms per centimeter cube. You similarly have a density of states function for the conduction band, which we plotted only near the band edge, because we said that the shape of the function is somewhat more complicated than the density of states function in the valence band. So that is why this portion is shown by a dotted line. And then the third postulate was that of these available states for the electrons at any temperature, only a fraction of the states are occupied, and this fraction is given by the Fermi-Dirac function. So that fraction we plotted, it looks something like this. So that is Fe. Comma T, because it is also a function of T. So this is a fraction of states occupied at any temperature. Now putting this information together, we wrote down an expression for the intrinsic concentration, and that was that Ni is given by integral Ne dE, that is the number of states available within an energy interval dE at E, multiplied by the fraction of these states which are occupied at any temperature. That gives you the number of electrons within the energy interval dE at energy E. So that is, if I were to take the conduction band here, that is the interval dE, the shaded area is the Ne into dE, and this small area here, that is Ne dE into the Fermi-Dirac fraction, and that small area represents the number of electrons or occupied states in the conduction band. So you integrate from EC to ET to get the total number of electrons. So that is how you get the intrinsic concentration of electrons. Now we said that if you make some approximations, then the formula for the intrinsic concentration can be simplified. So here in this formula the left hand side is occupied conduction band states at any temperature T. That is the concentration of electrons. Now the approximations we said we need to make to get a simple expression from here are: replace this by infinity. It makes no difference because here this Fermi-Dirac function rapidly goes to 0, approaches 0. So it does not matter whether you take Et as a limit or infinity as a limit. The next thing is, for this function, density of states function, use the parabolic approximation. Okay, so parabolic density of states approximation. According to this approximation, your state density is given by square root of E minus EC into some constant. That is a parabolic density of states approximation. And then for the Fermi-Dirac fraction, you use the Boltzmann approximation. So this is approximated as F B. We will write the symbol B for Boltzmann. Which would mean that the function is written as, so that is equal to exponential of E minus EC by KT with a negative sign. So we are writing f of Et as approximately equal to f of B Et, that is Boltzmann approximation of the Fermi-Dirac fraction, and that is given by this formula. So when you substitute this term here, that is the parabolic density of states approximation here, and then the Boltzmann approximation into this, and raise the top limit to infinity, then we have shown that, we have not done the detailed derivation, then we have said that the formula can be written as Ni equal to 2 pi mn kt upon h square whole power 3 by 2 into exponential of Ec minus Ef upon Kt with a negative sign. It is left to you as a homework to do the derivation. We want to interpret this formula physically. This is where we left in the last class. I have repeated this portion because this is very important part of the derivation in the energy band approach. So how do we interpret this formula? Let us denote this term by Nc, N suffix C, and let us try to interpret this constant Nc. Physically, what could it mean? As we have said, this Ni represents the occupied conduction band states. Let us look at this function. What does it represent? This represents the Boltzmann approximation to the Fermi-Dirac function at E equal to Ec and temperature T. So let me explain that part again. So Fermi-Dirac fraction is given by 1 by 1 plus exponential E minus Ef by Kt. if I want to get the value of this function at the conduction band edge EC, then all that I need is I substitute EC here instead of E. So this represents the fraction of states occupied within the energy interval dE at EC. Now if you were to take the Boltzmann approximation to this function, assuming EC minus EF is more than 3 times kT. So for EC minus EF more than 3 times kT, we will also use equal to, more than or equal to 3 times kT. This above function is approximated as this function, okay, because the one can be neglected. So here if you write for this, f of EC comma T is approximately equal to FB of EC comma T, and this is the Boltzmann approximation. So that means this term represents the fraction of states occupied for energy EC within an interval dE at any temperature. If this is so, and if this is the number of occupied states, okay, then it is easy to see that we could interpret NC as the number of available states at EC. Now please note, this is only an effective description, it is only an effective description, that is, it is not the actual description, okay. It turns out that when you work with the actual description and you come up with a simple formula, that simple formula if you want to physically interpret in terms of some kind of an effective description, then since this term represents the fraction of occupied states at EC at any t under the Boltzmann approximation, and Ni represents the number of occupied states, therefore it is evident that this can be taken to represent the number of available states at EC. So what it is saying is, what this formula is saying is something like this. Although this is the actual picture where you have the states distributed over energy here, in a simple representation of this we could regard this picture as equivalent to something like this. So this is an effective picture, effective band picture. So you have EC here and you have EV here, you have NC states, allowed states, all present at EC. This is approximation, that is interesting. All the NC states are as though they are present at EC. So how do I represent all the NC states at EC? Either I should use a delta function, it's like a delta function representation, okay. So it is something like this. So I will represent it something like this. The area under this function is NC per centimeter cube. Available states at energy EC, as though all are available at EC. This is an effective picture. And then if you want to know what fraction of these states are occupied at EC, what fraction of these the electrons are present, then all that you do is multiply these states by the fraction given by the Boltzmann approximation, okay. So that is why the NC is called the effective density of states at the conduction band edge, effective density of states at the conduction band edge. That is a physical interpretation of that constant NC. We will see a similar picture for the valence band edge, but before that let us look at one more point. We have said that this formula is derived under the Boltzmann approximation, apart from the approximation such as the parabolic density of states approximation. Now how do you know that this approximation is valid? For this approximation to be valid, your EF should be below EC by at least 3 times kT. Okay. Now how do you know that is true? So we have said one way of checking that is to now derive a formula for EF and then check whether indeed EF is below 3 times kT, which we will do it. But even before we do that, we can also just use simple logical reasoning to check if this will be true. So can we locate EF, the Fermi level in an intrinsic semiconductor, from simple reasoning? It turns out that we can do it as follows. So location of EF by simple reasoning. So look at the now band picture. I will show the EC, EV and the energy gap. Let us start with the definition of Fermi level at t equal to 0. The definition of Fermi level is that it is that level above which no level is occupied at t equal to 0 and below which all available states are occupied. Okay. So it is clear that the EF cannot be in the conduction band, because if the EF was here in the conduction band, then so we are talking at t equal to 0. And then we will consider what happens for higher temperatures. So at t equal to 0, supposing my EF was in conduction band, then what does it mean? That below EF whatever states are there which are allowed, they must be occupied. So which means I would have so many occupied states here, all the states which are available in this region. Above EC and below EF, some states are available because that is what our band picture says. So they must be occupied. So which means there must be conduction electrons at t equal to 0, which is not true. We know that at t equal to 0 there are no free electrons. So therefore your EF cannot be in the conduction band. Okay, so this means that EF cannot be more than EC. This is clear. Now let us see, can EF be in the valence band? If I assume the EF to be in the valence band, then again by definition of Fermi level at t equal to 0, all states above EF should be unoccupied, which means all the states which are in this energy range, available states, they should not be occupied. Now but we know that at t equal to 0 the entire valence band is occupied, because there is no way the electrons can become free, so they must remain within the valence band. They are all bonded to the atoms in the bond model. So in the energy band model, that means they are all in the valence band. So again EF cannot be within the valence band. So this is ruled out. So it is clear that the EF should be somewhere between EC and EV. It has to be within the energy gap. Fermi level is in the energy gap. That is what is clear from the simple analysis at t equal to 0. Now you go to higher temperatures. Where is the Fermi level likely to be? So start from t equal to 0. Let us say, supposing I were to assume my EF is here, away from the valence band but close to the conduction band within the energy gap, if EF was something like this. Now at t equal to at t greater than 0, the Fermi-Dirac fraction, if I were to find out based on this EF, it would be something like this. Using this Fermi-Dirac fraction, I can find out the number of electrons using our formula here. This is a formula like this, that is, I will take this fraction, multiply by available states and then integrate and so on. This is what we did. I will get some number of electrons. Now all these electrons have come from the valence band, they have to come from the valence band. So which means the number of unoccupied states in the valence band, should be equal to the number of occupied states in the conduction band. because electrons which have come to the conduction band for higher temperatures have come from the valence band. Now it can be easily shown that if your EF is close to EC and away from EV, using the formula for the Fermi-Dirac fraction, the number of unoccupied states that you can calculate in the valence band will be less than the number of occupied states in the conduction band. In other words, Ni will turn out to be more than Pi. Unoccupied states in the valence band indicate the hole concentration, and we have already said hole concentration is equal to electron concentration. Okay, we have explained why this is so. So translated into number of states, unoccupied states in the valence band are the holes. This should be equal to the occupied states in the conduction band in a pure semiconductor at any temperature. If these two turn out to be not equal for a certain choice of EF, then that choice of EF is not correct. Okay. Now how do we show that Pi will be less than Ni for this condition? For EF close to the conduction band, very close to the conduction band, this will be the result. How do you show that? That is very simple. The number of holes is given by Pi equal to integral Ne dE into 1 minus Fe. Integrated over the valence band edge. This is the formula for Pi. From analogy to the formula for Ni, all that you have done is, instead of F Fermi-Dirac fraction indicating the occupied states, you are taking 1 minus the Fermi-Dirac fraction, because that represents unoccupied states. Other part NEDE is the same as in the formula for Ni. This represents the number of available states in energy interval dE at energy E. So this gives you, if you integrate this, you will get the unoccupied states in the valence band. Now look at the function, Fermi-Dirac function, and 1 minus the Fermi-Dirac function. So your Fermi-Dirac function is, at any temperature T, is, let us say, something like this. Zero, 1, and this is half. Suppose this is Fe, this is E, and this is Fe. So I will write Fe here. If this is Fe, 1 minus Fe, how is it? It is a symmetric function which is given like this. Okay, something like this. That is, it is a reflection of this function around about this line. You just reflect it. That is 1 minus Fe. So now if I come back to this diagram, if I were to sketch 1 minus Fe here, it would be something like this. So this is f of E, and here this is 1 minus f of E. Now you can very clearly see that you put the density of states function here, parabolic density of states approximation, allowed states. Now you multiply f of E into Ne, this is Ne, and you get this area. Integrate. multiply and then integrate, then you get this area. You do the same exercise here. This is Ne in the valence band, this is 1 minus Fe, and that is the area, which is the unoccupied states. Ne dE into 1 minus Fe integrated over the valence band is that area, this area. So it is very clear, if your EF is close to the conduction band edge, then this area will be less than this area. This area is Pi and that area is Ni. In fact, if the parabolic density of states function for valence band and conduction band, if these two shapes were exactly identical shape of these functions, meaning in this parabolic density of states approximation, the constant A, the parabolic density of states function is given by A into square root of E minus Ec for the conduction band. For the valence band it is again a constant into square root of Ev minus E. So if the two constants in the density of states functions for the conduction and valence bands, if they are exactly same, okay, then it is very clear that this area Pi will be equal to Ni if Ef is exactly in the middle of the energy gap. From this diagram it is very clear that I will get Pi equal to Ni if Ef is exactly in the middle of the energy gap, provided this function and this function, the constants were the same in the parabolic functions. So they are slightly different because the effective masses of electrons and holes are slightly different. So from here we can see that Ef will be very close to the middle of the energy gap for t greater than 0, in order that Ni be equal to Pi, Ni remain equal to Pi. Now if Ef is very close to the middle of the energy gap, then what is the distance between Ef and Ec? The energy gap in silicon is 1.1 electron volt. Half of 1.1 will be 0.55. The value can be 1.1 or 1.12 depending on from where you have taken the data. Let us say it is 1.1, okay, to first decimal place, then it is 0.55 electron volt, that is Ec minus Ef. Now what is kT at room temperature? 0.026 electron volt. So 0.026 into 3 times kT, 0.026 into 3 is 0.078 electron volts. So you compare 0.55 electron volt and 0.078 electron volts, right? So you will always find that Ec minus Ef in a pure semiconductor like silicon and in many other semiconductors, okay, will always be more than 3 times kT at any temperature, and therefore Boltzmann approximation is valid, okay. That is the reason why the Boltzmann approximation is valid, and that is why this effective density of states picture, where you assume that there are Nc states available at Ec, that is the picture of the conduction band. This effective density of states picture is therefore quite valid, okay, and the Boltzmann approximation is valid here, and this formula Ni is therefore fairly accurate for all practical purposes. Now we can write down a similar formula for Pi, okay, and get an exact expression for Ef. Now we have placed Ef by logical reasoning to be close to middle of the energy gap. It is not exactly at the energy gap, middle of the energy gap, because the effective mass of electrons and holes is not the same, okay, or the parabolic density of states functions for conduction band and valence band are slightly different, their constants are slightly different. So we need to exactly find out what is Ef, okay, and once you eliminate Ef from this equation, then you have a formula for Ni, because right now what is happening is Ni is still a function of Ef, and unless you know what is Ef, you do not know what is Ni. We want to calculate Ni at any temperature. So based on whatever discussion we have had now, we can write down an expression for Pi. So Pi, we have written it here, is equal to integration over the valence band of the function Ne dE into 1 minus f of e comma t. You use Boltzmann approximation to the Fermi-Dirac function, and then use parabolic density of states approximation here, and the bottom of the valence band you replace by minus infinity. Okay, so this is replaced by minus infinity, and then your result will be exactly analogous to this. So I can write down the result for Pi simply from the result of Ni. All that I have to do is replace Mn by Mp. You replace this suffix n by p. Replace Ec by Ev, and also you interchange Ef and Ev. Okay, so it should, instead of Ec minus Ef, it should be Ev minus it should be Ef minus Ev, because this term should be positive, and you know the Fermi level is below conduction band edge but is above the valence band edge. So your formula for Pi would be, it is the same as the formula for Ni with the replacements Mn replaced by Mp and Ec minus Ef replaced by Ef minus Ev. So I can write Pi is equal to 2 into 2 pi Mp kt by h square whole power 3 by 2 into exponential Ef minus Ev by kt with a negative sign. If students have some difficulty in trying to remember whether it should be, let us say in this formula for Ni, Ec minus Ef or Ef minus Ec, okay, they must know the physical interpretation of the formula. That is why we have taken a lot of time to interpret this formula. Once you know the physical interpretation, this problem is not there, because you know that this represents a Fermi Boltzmann approximation to the Fermi-Dirac fraction. So it is a fraction. It should be less than 1, that there is no doubt. In fact, it will be much less than 1. Okay, so if that is so, that is why the negative sign is kept outside and the term inside the bracket should be positive. Okay, so once you know this, you can remember this formula, whether it is Ec minus Ef or Ef minus Ec, and similarly for Pi. Now we can eliminate the Ef between these two results by simply multiplying Ni and Pi. When you multiply, the Ef will get cancelled and we will get the result Ni Pi is equal to 4 into 2 pi kt upon h square whole power 3 into Mn Mp whole power 3 by 2 into exponential of Ec minus Ev upon kt with a negative sign. That is the result. The Ef has got eliminated. If we were to write it using the symbol that we have used, namely the effective density of states in the conduction band is given by n suffix c. Okay, now you use an analogous representation, there will be an effective density of states for the valence band. Okay, that will be given by n suffix v. Why n suffix c is different from n suffix v? Because Mn is different from Mp, that is the only reason. So I could write this formula, that this term as Nc into Nv, and I recognize the fact that Ec minus Ev is nothing but the energy gap. So this quantity can be written as exponential of minus energy gap by kt. And further, I recognize that this term Ni into Pi, since Ni is equal to Pi, Ni should be equal to Pi in a pure semiconductor or intrinsic semiconductor. So I can write this as Ni square or Pi square. convention is you write Ni, okay. You can write Pi square also, you write it as Ni square. So now I get the relation Ni square is equal to Nc Nv into exponential of minus energy gap by kT, okay. And therefore I can write the formula Ni equal to square root Nc Nv into exponential of minus Eg upon 2 times kT. So that is the result. For the intrinsic concentration as a function of temperature and the physical parameters such as energy gap and effective mass of electrons and holes. Now this result is what we have shown earlier. I will show you the slide. Before I show the graph, let me summarize the quantities that are there in the energy gap, energy band diagram or energy band model of silicon. So what are the parameters that you need to know? So here first important parameter is band gap or energy gap, Eg for silicon 1.12 electron volts, for gallium arsenide 1.42 electron volts. So you can take down, as I mentioned, these parameters and their values here. Then the other important parameter is electron affinity, which is the difference between the vacuum level and the conduction band edge Ec. So E0 minus Ec, that is the symbol chi, that is 4.05 electron volts for silicon, 4.07 for gallium arsenide. So the semiconductors, different semiconductors have very close electron affinity values. Then the intrinsic concentration Ni, if you substitute in the formula, okay, you will get these values. Now it turns out that if you substitute the effective mass values, the energy gap values and so on, you don't get exactly this number, okay. So what the number given here is the value that is obtained from measurements. So in practice you may get, instead of 1.5, say a value of say 1.1 or 1 or something like that. In fact, you can do this as a homework. Next slide will give you the effective mass of electrons and holes. You can use those values and you can use this energy gap that is given here, okay, and try to estimate the concentration. This is because this kind of problem arises because you are independently measuring these parameters. Energy gap is being measured by some particular approach, okay. The effective mass of electrons and holes are being measured by some other approach, right, some experiment. And so when you want to put it all together, some inconsistency will be present. So normal practice is, whichever parameter you want to use, you use its experimental value. But the formula is very important, because now what you can do is you can use this value of Ni for room temperature. So these values that are being shown are valid at room temperature, okay. Temperature is 300 K. So normally if it is not indicated, you must take this value as 300 K, okay, the temperature. So you can use this value of Ni at T equal to 300 K, and then you can use the formula to find out the value at any other temperature. So that is the way you must calculate the concentration at any other temperature, okay. So that means, for example, here Ni is given by this. If you know Ni at T equal to 300 K, then it means you know Nc Nv at, and you know Nc Nv at 300 K, okay. So you must write an expression for Ni as a function of temperature. You can see what kind of expression you get here. You will get an expression of the form Ni is given by some constant B into exponential into T power 3 by 2 into exponential of minus Eg by 2 times kT, where the constant B accommodates the effective mass of holes, electrons and so on. Now you know the value at 300K. So you know Ni 300K. Use this value to get the constant B, which is independent of temperature, and then use that value, that constant, and you can find out Ni at any other temperature. So Ni 300K, in terms of Ni 300K, if I want to write down, so Ni, any temperature T by Ni 300K will be given by, as you can see here, T by 300 whole power 3 by 2. This B will cancel because it is independent of temperature, into exponential of minus Eg by 2K into 1 by T minus 1 by 300. If this is, I can rub this off a little bit here. So that the confusion is not there. Okay, this is the formula. Now this is how you can estimate Ni at any other temperature. So this is the approach that one needs to follow if you want results which are close to the experimental values. Now let us look at the other parameters, such as effective density of states. At the conduction band edge, it is Nc. These values are given here. For silicon, 2.8 and 10 power 19. So order of effective density of states is 10 power 19 in silicon. Nv slightly different, 1 into 10 power 19 per centimeter cube. It is also important to remember the units. These values for gallium arsenide are given here. So what you find, the difference between silicon and gallium arsenide is, in silicon Nc is more than Nv, but in gallium arsenide Nc is less than Nv. It all depends on the effective mass of electrons and holes. So gallium arsenide has a much lower effective mass of electrons than silicon. Then you have the dielectric constants given here, epsilon r. This slide now shows you the effective masses. What is important to note here is, again, these are values at T equal to 300K. What is important to note here is, you have two types of effective masses: conductivity effective mass and density of states effective mass. That is, the effective mass that is used varies with the physical situation. This is because it is an average value. Now the average is not necessarily the same in different situations. Okay? This is not very difficult to understand. If you want to calculate the average of something, it depends on the situation. How you average also is an important thing. It is a weighted quantity. Okay? It is a weighted average. So specifically, what is important to see here is, if I take the density of states effective mass, which is the value that should be used if you want to estimate Nc or Nv, effective density of states, that is where this is to be used. Then silicon, the electron is heavier than the hole. Okay, that is what is important. The electron is heavier than the hole. Whereas if you take the conductivity effective mass, conductivity situation for estimating the resistivity and so on, you want to find out mobility. Later on we will see how this effective mass is useful to find mobility, for example. That is movement of the carrier in response to an electric field. In that context, this effective mass of electron is less than that of holes. So electron is lighter than the hole for conductivity situation. Intuitively this is more satisfying. Okay, easy to understand, because the movement of the hole is actually movement of bound electrons, and therefore that movement is going to be slow. So in density of states effective mass, you should not invoke the concept of movement. Okay, it is some different average used to represent the quantum mechanical situation. We will not discuss this point any further. The only thing you need to remember is effective mass depends on the situation. Okay, so you must use the appropriate effective mass. The values are shown here for gallium arsenide. this value here is not shown because the exact value there is no agreement. Okay, that is all what it means, not that there is no whole effective mass for gallium arsenide under conductivity situation, it is not that. Okay, and now next we come back to the behavior that we wanted to explain using our formula. So Ni versus temperature. Okay, so log of Ni versus reciprocal of temperature, it is a straight line. Now this is very clear from our formula. Let us look at the formula again here. So Ni is equal to square root Nc Nv into exponential of minus Eg by 2 times kT. If you take the log, then what will happen is you will get log of Ni is equal to log of, okay, I think I will use the simplified representation of this formula, that is I move here. Ni is given by B into T power 3 by 2 into exponential minus Eg by 2 kT. So log of Ni is equal to log of B plus 3 by 2 log T minus Eg by 2k times 1 by T. Now this log of T, this is dependent on temperature, but this variation with temperature is very, very small because it is logarithmic dependence on temperature, whereas as this particular term which depends on 1 by T, it varies much more rapidly than this term. Okay, and that is why what you have is log of Ni versus, if you plot 1 by T, so log of Ni versus this 1 by T term would be a straight line. This effect of log of T you will not see here in your line. That is why it almost looks like a straight line, even though this is, strictly speaking, this term is present, its effect is not so much, does not show up in the variation. And this also shows that the slope of your straight line is Eg by 2 times k. So the slope depends on the energy gap and the Boltzmann constant k. So Ni on the log scale and 1 by T, the slope is equal to minus Eg by 2k. So you can use the slope to get the energy gap of the semiconductor. This is the approach that is used to get the energy gap from the measured concentration. Okay, so now we have got a model for the behavior. Now final step, we will write down the formula for EF. So from Ni and Pi I can get EF. I just have to equate Ni to Pi. You equate Ni equal to Pi and then I can get EF as EF is equal to, you can do the derivation yourself, I will write down the result, EC plus EV by 2, that is middle of the energy gap, minus kT into ln of Nc by Nv square root. That is the location of EF. So now you know that Nc and Nv are not very different, particularly if you are going to take the log of this quantity. Okay, this quantity is not going to be really significant. So it is almost EC plus EV by 2. And this quantity here, this term depends on temperature, but again this dependence on temperature is negligible because this quantity is again small. If you take silicon for example, the Nc value was the Nc value is 2.8 and Nv is 1, so square root of 2.8 and you take log of that, it is really going to be very small. Okay, So EF is approximately equal to EC plus EV by 2. It's the middle of the energy gap. So with this we have completed the discussion on the intrinsic carrier concentration of the semiconductor, and next we will take up the model of the extrinsic semiconductor or the doped semiconductor and try to explain the carrier concentration versus temperature behavior. So let us see if there are any questions now.
Sir, according to the formula derived for Fermi level in intrinsic semiconductor, the Fermi level is a function of temperature. Then how is it that the slide showing Fermi Dirac function at various temperatures appear to have a Fermi level independent of temperature?
Let us look at this slide. If you note carefully, the y-axis is E minus EF and not E. That is, we are plotting the energy as with reference to the Fermi level and not the absolute energy. So when you take E minus EF on the y-axis, then any variations in EF need not be shown on the graph. If however you plot the function as shown on this diagram, where we are plotting the energy, electronic energy on the y-axis and the Fermi Dirac function as a function of the electronic energy. Here the picture would be something like this. Variation of Fermi level with temperature will be seen. Now this is the line which represents the Fermi Dirac function for a temperature T1. For a higher temperature T2, if I were to show the function, it will be shown by this line. Notice that the Fermi level for T2, which is here, this is the line showing the Fermi level for T2, this is lower than the line shown for Fermi level corresponding to T1, which is this one. So EF2 is below EF1 for T2 greater than T1. This is because according to the formula we derived here, that is EF equal to EC plus EV by 2 minus KT into ln of square root NC by NV, we can see that as temperature increases, because of this term the Fermi level moves down. So when you plot the Fermi Dirac function as a function of absolute energy, the variation in Fermi level with temperature will be seen. Whereas if you plot the Fermi Dirac function with reference to with respect to E minus EF as shown in this slide, in that case the variation in Fermi level with temperature will not be seen. Any other question?
Sir, you have given several analogies to explain the concept of holes, splitting of energy levels, density of states function and Fermi Dirac function. Is there any analogy to explain the fact that electronic energy can only vary in discrete intervals and not continuously?
Yes, there are several analogies to explain this fact. A simple analogy is as follows. Supposing there is a staircase like this and there is a ball. Now the question is, at what heights can the ball exist on this staircase? So you know that the staircase can either be, the ball can either exist at this particular staircase, that is this region, or this, or this, or this region. It cannot exist, for example, in these vertical portions of the staircase. You can't have a ball, say, existing somewhere here. It can't rest there. So you can see here that the ball can only exist at discrete heights. There is another example which is much more interesting, and suppose there is a street and this street has signals at regular intervals. Let us say the distance between two consecutive signals is d. The signals turn green at interval of t minutes. Imagine that there is a car which wants to pass through the street uninterrupted, even when you have the signals turning red or green. What are the speeds in which the car can move so that it will not be interrupted by the signals. Now this is the question. Now it can be shown that the speed of the car is given by d by nt, where n is an integer. Let us see why this is so. So the speed of the car can only vary in discrete steps. So the car is only allowed these particular speeds. Let us take n equal to 1 case. What does it indicate? Now the car is moving, the signal here has turned green, it has passed this signal. After a time t minutes, it is right here when this signal is turning green. So it has crossed a distance d in time t. So since the signal has just turned green, it can move uninterrupted and go to the next signal, and this will continue. So you see the speed of d by t, that is n equal to 1, the car moves uninterrupted. Now another speed that is allowed is n equal to 2, that is the speed is equal to d by 2t. Now you see what is happening in this case, the speed is half of the speed for n equal to 1, that is the car has passed this signal when it is green, and next time this signal turns green, the car is exactly halfway here. So when it comes here, the signal turns green for the second time, and then again the car moves uninterrupted. So this is the way the car can continue moving. It can be shown in a similar manner that for n equal to 3 also the car will move uninterrupted. So you are allowed speeds given by d by t, d by 2t, d by 3t and so on. So the car speed can only change in discrete intervals or discrete steps in this particular situation. So like this, there are many situations where the parameters can only assume discrete values. With this, we have come to the end of the discussion on intrinsic semiconductors.